My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Good afternoon to all. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology has started its online program, including online International Physics webinar. We have successfully completed our 207th International Physics webinar, including 3 Nobel laureate speakers. And today, we would like to welcome you all to a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Yukawa Institute for Theoretical Physics, Kyoto University, Japan. And we have with us here today Dr. Shinji Mukohyama, Professor Yukawa Institute for Theoretical Physics, Kyoto University, Japan. And I'd like to welcome our speaker. So, sir, good afternoon, and thanks for accepting our invitation. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. So before going to you, I'd like to inform you, I would like to introduce you with all of our students and viewers. So dear students and viewers, I think you have already come to know the title of this International Physics webinar. Title is the Gravity Beyond the General Relativity. I think you will enjoy this exciting webinar. And our speaker is Dr. Shinji Mukohyama, Professor, Yukawa Institute for Theoretical Physics, Kyoto University, Japan. So if we see his educational and professional career, you can see Dr. Shinji has completed his bachelor degree in physics from Kyoto University and master's at the same from the same university, and PhD also same university in 1999. And we can see his employment record that he has started as a research assistant at the same Kyoto University, Yukawa Institute, and then he got a fellowship from JSPS and worked as a fellowship of JSPS at the same university, Kyoto University. Then he got a CITA National Fellow at the University of Victoria, and then he got JSPS and went Harvard University and stayed there 2001-2003, and got postdoctoral fellow and worked as a postdoctoral fellow at the University of Harvard, and then he joined as a assistant professor at the University of Tokyo, and currently he also working as a professor at the same university. And we can see he got different awards, and we can see that he got his first award as a young scientist from the award of the Physical Society of Japan, and in 2007 and 2009, and in 2014 he got language award from the Institute of Language de Paris, and in 2017-18 he awarded by the University of Tours as a visiting professorship. So thanks all of your patience. It's time to go to our speaker. Sir, it's your time.
Okay, thank you very much. Thank you for kind introduction. Okay, so today I'd like to talk about gravity beyond the general relativity. So this is basically an introduction to modified gravity. Okay, so let me start. Okay, first introduction. Basically, so the motivation for modified gravity. Okay, there are several things. First, motivation comes from IR modification. Okay, so the motivation for IR modification, namely the long distance and long time scale modification. So the motivation comes from gravity at long distances, of course, and starting from the flattening galaxy rotation curves and the dimming supernova. There are many interesting phenomena. Okay, and people usually try to explain these interesting phenomena by introducing new form of matter, namely dark matter, and new form of energy, namely dark energy. This is the usual story, but there was something similar in the history when we look at the science history in 19th century. So people discovered that Mercury was doing something interesting, namely the precession of helium was observed. Then some people try to explain this interesting phenomena by so to speak, dark planet, okay, unseen planet, and this was called Vulcan. Okay, and this idea was somehow, so at some point, up to some point, it was successful, but it didn't explain everything. So the right answer wasn't dark planet. And but actually, there were some people who claimed that they discovered this dark planet, and of course it was not the correct, real discovery, and discovery was false. And so the right answer wasn't dark planet. Okay, and it was change gravity from Newton to GR that explained this interesting phenomenon. Okay, so this was the beginning of the success of general relativity, namely the Einstein theory of gravity. Okay. So considering this historical fact, I think it's natural to ask whether we can address mysteries in the universe by modification gravity. For example, dark energy, dark matter, inflation, Big Bang singularity, and cosmic magnetic field, perhaps. And so if we can replace some of them by modification gravity, that would be great. Namely, we may be able to tackle these difficult but interesting questions in a different way. And if we are lucky, then maybe we can solve it. Okay. Even if we cannot solve it, then we may have some new ideas by modification gravity. Okay. So this is the first idea, first motivation. Okay. And second motivation comes from quantum gravity, namely the unification of quantum theory with general relativity. Okay, we want to unify them, but it's not easy. And most of people believe that we need to modify general relativity at short distances, okay, to unify gravity with quantum theory. Okay. So this is the second motivation. And for example, superstring theory, or for example, Hodge-Blix gravity, those theories modify general relativity at short distance in order to unify general relativity with quantum theory. Okay, so for me, superstring theory is one of modified gravity for this reason. Okay, and third reason to study modified gravity comes from the GR itself. Okay, so we want to understand general relativity, and in order to do that, for example, suppose that the GR is correct description of the gravity, at least at long distance. At short distance, probably we need to modify. But at long distance, maybe, there may be a possibility that the GR is a correct description. Even in that case, in order to prove it experimentally or observationally, I think one of the best way to do that is to constrain the possible deviation from GR by experiment or observation. In order to do that, I think it's very useful to have a prediction of modification gravity. Namely, that we want to know how observables or changes when we modify gravity. Then we can constrain those deviations from GR by experiments or observation. After all, I think one of the best ways to understand something may be to break it and then to reconstruct it. Okay? So after modification, and then we see how observable changes, and then we so constrain those deviation by experiment and observations, and it may turn out that GR is correct, and then in that case we constraint become better as we progress, and then later we understand GR better. And also theoretically, after modification of gravity, and actually modification of gravity is not so easy if we try to do it in a consistent way. In order to do that, by doing that, we learn GR itself. Okay, so this is the third motivation. Okay, so from this third motivation, I think it's better to understand also in order to modify gravity, by modification of gravity, we understand GR. And also, in order to modify gravity, we need to understand GR itself. Okay, so this is the third motivation. Okay, and when we have gravity beyond the GR, I think we need to put some conditions for good theories. Otherwise, whatever is different from GR would be modified gravity or alternative theory of gravity. So we need to put some conditions, I think. Okay. First, this is my personal viewpoint. So different people may have different opinions, but I hope you agree. Okay. So the first, I think theory should be consistent. For example, we need to avoid the so-called ghost instability. Otherwise, theory doesn't make sense. Okay. Second, theory must be experimentally viable. We need to satisfy the many constraints. For example, solar system test or tabletop experiments and so on. Otherwise, we cannot, for example, discuss about the mystery of the universe by modification gravity. Okay. Third, it would be great if the theory is predictable. Then we can compare the predictions with experiments and observations. Okay. So, for example, if the theory is structure of the theory is protected by symmetry, then we can make a robust prediction. Okay. Even after that, there are many theories, and today I think I'm going to talk about so one to no. Okay, so there are several examples that I have been working on, and I think today I'll talk about this effective field theory approach for scalar tensor theory and massive gravity, and what else? Yes, I think these two. Okay. Before that, I'll talk about the so-called PPN formalism and GR itself and Lovelock's gravity. Okay. Okay. So let me explain some examples before talking about them. Okay. So effective field theory approach for scalar tensor theory is motivated by IR modification, namely long distance and long time scale modification, and to address the mystery of dark energy and dark matter. Okay. Massive gravity is also IR modification gravity, but this comes from the more kind of fundamental question, like can graviton have mass? Okay. Namely, the spin-2 field can have a mass or not. Okay. And the third one, Higgs gravity, although I don't have time to explain this today, comes from UV modification gravity. Namely, the motivation is quantum gravity. Also, superstring theory is motivated by quantum gravity, and also unified theory. And this is also UV modification gravity. Okay. Then today I will talk about these two. Okay. And before starting, I'd like to remind you one important and interesting result that we have recently. So this is an implication of this event, a gravitational wave event, GW170817. On gravity theories and late time. Okay, so the observation by the observation, so the almost the same time, simultaneously the gravitational waves and the gamma rays from neutron star binary coalescence was discovered, and then we know that the speed of gravitational waves and the speed of light are almost the same. Okay, a difference should be less than 10 to minus 15 or something like that. Then this has many implications to gravity theories. Okay? For example, in the so-called Horndeski theory, which is a scalar tensor theory with second-order equation motion. Originally, there are 4 free functions, but only so now 2 functions are strongly constrained, and this event almost killed these two functions. But still, we have 2 free functions, and also recently, so one of these 2 remaining G3 was analyzed, and this may also be constrained by the gravitational waves dark energy interactions, and also similar consideration was studied for the so-called generalized Proctor theory, which is vector tensor theory. Okay, so the free functions, a number of free functions is now reduced. Okay, and also for the Higgs gravity, which I briefly explained, this is a renormalized quantum gravity, and in this case, the speed of gravitational waves is controlled by the coefficient of the 3D curvature, and this is strongly constrained. So this indicates that probably there should be an IR fixed point with this property, and if there is such a thing, such a IR fixed point, then we need to ask whether how to speed up the RG flow toward this in order to satisfy this condition. So yes, we have a good question to ask. Okay. And then for the ghost condensate, which is the EFT of scalar tensor theory, which I will explain now later. Okay. So for this, fortunately or unfortunately, this doesn't give us the additional constraint. For massive gravity, there is upper bound coming from this, which is about 10 to minus 22 electron volt for the graviton mass. Okay, so this is very strong, but still not as strong as what we expect from the acceleration. We not explain the acceleration. We need to have a much smaller value, small value. Okay. Anyway, so there are many implications. Okay. Also, I have to mention that all gravity theories, including general relativity, kind of suffer from the so-called cosmological constant problem, this is a problem of a small number, which is as small as 10 to minus 120. So this is much stronger than this. And this is so difficult that the people usually try to ignore. There are some brave people to tackle this, but many people try to actually ignore this. But this one is difficult, but not as difficult as this. So maybe we can tackle this first. After that, maybe we can try to understand this. So I think this is a very good timing to think about alternative gravity theories. Okay, because we have experiments to probe those modification gravity. Okay, so let's start. Okay. By the way, if you have questions at any time, please stop me. Okay. So now I'd like to talk about GR itself, because in order to modify gravity, GR, we need to understand GR itself. Okay. So GR is based on the so-called equivalence principle. So let me start with this. Okay. So equivalence principle tells us this. So that if we consider uncharged test body, and then the initial event in space-time and initial velocity, then the subsequent trajectory is independent of internal structure and composition. Then we say that the equivalence principle holds. Einstein assumed the so-called Einstein's equivalence principle, and which consists of two things. One is weak equivalence principle valid, namely this one. And second, outcome of any local non-gravitational test experiments is independent of the velocity of freely falling apparatus and of the time and the position of the universe. Okay. Basically, this says that gravity is equivalent to acceleration, at least locally. Okay. Then this means that if we assume this Einstein's equivalence principle, then this means that we should have a metric, the so-called metric. Okay. Metric is a symmetric tensor which is non-degenerate. Okay. Because this principle means that gravity is acceleration. So if we free fall, then the gravity is absorbed. Namely, in the local free falling frame, the special relativity should be valid. Namely, we have something that reduced to Minkowski metric eta mu nu, and something should be tensor. Okay, so there should be a tensor that reduced to Minkowski metric in the local free falling frame. Okay, so we call this tensor a metric. Okay, so the Einstein's equivalence principle implies that there is a metric. Okay, so a theory with a metric is called the metric theory. By the way, this argument does not exclude existence of other metrics and also the field that is responsible for other fields that is responsible for gravity. For example, scalar field or vector field. But there should be at least one metric. Okay, and Einstein theory assumes this Einstein's equivalence principle. So we have metric, and on top of that, we assume that the gravity is described by the metric only. Okay. So then the action can be written in this way. So the action is written as an integration over whole space-time of a scalar field multiplied by square root minus g. Okay, g is a determinant of metric. Okay, and then the question is how to construct this scalar L. Okay, Lagrangian. Okay, and this should be made of metric and its derivative only, because we assume this. And up to first derivative, we have only constant. Okay, the first derivative is basically a Christoffel symbol, but Christoffel symbol is not tensor. So we cannot construct the scalar made of first derivative. So we have just only a constant. Up to second derivative, we have scalar made of g mu nu and the curvature. Okay, so the rich scalar. Okay, and then we can go on to higher order in derivatives. Then this scalar L is made of a constant and a scalar curvature and a scalar curvature square and so on. Then by introducing scale M, we have this, okay, where C1, C0, C1, C2, and so on are dimensionless constant. Okay. Then if we are interested in the low energy physics, then we can truncate at terms with the two derivatives, for example, okay, because higher order terms are suppressed at low energy. Then we have this. This is nothing but the so-called Einstein reduction, which describes Einstein's general relativity. And here we introduce M Planck and lambda in this way. And by the way, the so-called cosmological constant problem is mysteries why this combination is much smaller than 1. Okay. Actually, this combination is as small as 10 to minus 120. Okay. So we don't know the reason. Okay. Having the action, we can compute the equation motion by taking variation with respect to metric. Okay. I skip the details of the computation, but we get this variation. And here G mu nu is a capital G mu nu is Einstein tensor. Okay. So by adding matter and taking the variation of the matter action with respect to G mu nu, we get Einstein equation. Okay. So this describes gravity in the Einstein theory. Okay. Here G Newton is given by this combination. Okay. We now know GR, and here I'd like to explain how we can compute the number of degrees freedom in general relativity. Okay. We know that there are gravitational waves in our universe, and there are plus modes and cross modes, and we saw that there are 2 degrees of freedom in general relativity. So we want to do this in a non-linear way. Okay. So let's start with the 10 metric components. Metric is here. Okay. This is a 4x4 symmetric tensor, so that we have 10 components. Then in order to count the number of degrees of freedom in a non-particle way, it's convenient to employ the Hamiltonian formulation. Namely, we go to the phase space. In order to do that, we multiply 10 by 2, so we have a 20-dimensional phase space at each point. Now, in order to do that, the so-called ADM decomposition is useful. And so that we decompose the metric in this way. Okay, so we introduce lapse, shift, and 3D metric. Okay, I and j round from 1 to 3. So that we have 1 component from here, 3 components from here, and 6 components from here. Okay, so in total we have 10 components. Then plugging this to the Einstein Heat reduction that we derived with the zero cosmological constant for simplicity, then we get this. Here, Kij is defined in this way, so-called extreme curvature. So this includes the time derivative of the 3D metric, this one here, but that doesn't include the time derivative of lapse or shift. Okay, this is a special derivative. And this is a 3D curvature, so that this includes the special derivative of Hij, but nowhere there is no time derivative of lapse or shift. Okay, so this means that when we compute the moment conjugate to lapse and shift, they are zero, identically. And these equations are algebraic equations in the phase space, and they are called constraints. Okay. All constraints are actually independent of n and ni. So when we compute the Poisson bracket between, for example, this one and any constraints, then they vanish. Okay. So in this case, we call that these constraints they are first class. Okay, let me explain what first class is and what second class is. Probably many of you know. And as we know, as always, first class is better than second class in the following sense, in this case. Okay, so second class constraint reduces one phase space dimension. Okay, because this constraint is algebraic equation, so that effectively reduce the number of dimensions of phase space. Okay, but second class reduce only one. On the other hand, first class constraint reduce two phase space dimensions. Okay, so in this sense, this is better. Okay. Also, first class constraint is always associated with symmetry, and because 2 is 2 equal 1 plus 1, so that this is equivalent to pair of second class constraints. Okay. Please remember this. So that they reduce each of them reduce 2 phase space dimension. Okay, we started from 20, and this reduced 2, and this we have 3 of them, and in total 4. So 4 by 2 equal 8. Okay, 8 dimension is reduced. And on top of that, we have more first class constraints because general relativity enjoys symmetry. Okay, diffeomorphism invariance. We can change coordinates, and we have 4 coordinates. So we have 4 generators of 4D diffeom. Okay, each of them is first class constraint because this is associated with symmetry. Okay, in total, we have 4 plus 4, namely 8 first class constraints. Each of them reduce the number of phase space dimension by 2. So the 20 minus 8 times 2 equal 4. Okay, so we have 4-dimensional physical phase space at each point. Okay, this means that we have 2 local physical degree freedom. Okay, I mean when we started from 10, we multiply by 2. So in order to go back to configuration space, we need to divide 4 by 2. Then we get the 2 local physical degree freedom. Okay, so number of degree freedom in GR is 2, corresponding to transverse stressless gravitational waves. Okay, so this is fully nonlinear analysis. Okay, so we now know that the number of degree freedom is 2, and here I'd like to explain briefly about the so-called Lovelock theorem, telling us about the uniqueness of GR. Okay, so this is the introduction to modified gravity. So we want to modify GR. Okay, but under certain conditions, we can prove that the general relativity is unique. So if we assume certain conditions, we cannot modify GR at all. Okay, so therefore, these conditions tell us what to do in order to modify gravity. Okay, so let me explain this. Okay, so Lovelock theorem assumes these 4. Okay. This theorem is talking about some equation motion for the metric, so that we talk about some symmetric tensor, which is supposed to be equation motion for the metric. Okay, so A mu nu. Okay, metric G mu nu, small g mu nu, and this is supposed to be equation motion for G mu nu. Okay, so this is assumed to be symmetric, and this is assumed to be a function made of metric and first derivative of the metric and second derivative of the metric. Okay, and also it is assumed that the divergence of this tensor is 0. Okay, and here this represents the covariant derivative. Okay, and also we assume that the number of dimensions is 4. Okay, because we are living in 3 plus 1 dimensions. Okay. And then this theorem tells us that this tensor A mu nu is a linear combination of Einstein tensor and the metric itself. So this tells us that the GR is unique. So this is by setting this to be 0 or by setting this to be equal to matter contribution, we get the Einstein equation. Okay. So let me explain the motivation for these 3 assumptions. I mean, fourth condition is of course obvious because we are living in 3 plus 1 dimension. Okay, and the first one is also obvious because this is supposed to be equation motion for G mu nu, and G mu nu is symmetric. So this should be also be this also should be symmetric. Okay, and the second condition, this one comes from this. Okay, if the equation motion depends on third or higher derivatives of the metric, then the number of degree freedom tends to increase. We don't want to do that. Okay, so we restrict our consideration to the equation motion which depends on only up to second order derivatives. Okay, and the third condition comes from this. Okay, so this is basically the Bianchi identity. Okay, and if the A mu nu is derived from some action, I mean this theorem doesn't assume the existence of action, but the motivation comes from the action. Okay, if we have action, and if action is diffeomorphism invariant, namely the invariant and the coordinate change, then this follows automatically. So we assume this, and also Einstein, yes. Okay, so then the GR is unique. Okay, and actually this comes from the some more mathematical theorems, but probably I'll skip this. Yes. Okay. And but please remember these conditions. Okay. Okay. So the this theorem, Lovelock theorem, tells us how to go beyond GR. Okay. So this theorem assumes 4 dimensions, and so gravity is described by Riemannian or pseudo-Riemannian geometry, and the metric is is only physical field. Okay, and therefore, in order to modify GR, we need at least one of the following things. Okay, so extra dimensions, or extra degree freedom, or Lorentz violation, or non-pseudo-Riemannian geometry. We need at least one of them. And Lovelock himself found a kind of modified gravity by going to the extra dimensions. Okay, and this is called Lovelock gravity, but probably I'll skip this. And he found the equation motion like this, and also the action that leads to this equation motion. Okay, and this theory is called Lovelock gravity. And the first two are Einstein-Hewitt action. And first one is Einstein-Hewitt action. Okay, and the second one is called Gauss-Bonnet term. Okay? That exists only in higher dimensions. Okay, in 4 dimension we recover general relativity, and in higher dimension we have a modified gravity. Okay. Okay. So let me go on to the after learning general relativity and straight for the generalization of GR, which is called Lovelock gravity. I'd like to briefly mention about the so-called PPN formalism, parameterized post-Newtonian. Okay, so this tells us, so that we want to modify GR in order to address either mystery of the universe or quantum gravity, or to test gravity, to test GR. But of course, it does not make sense if the theory is already excluded by experiments. Okay, and this parameterized post-Newtonian formalism help us to see whether your favorite theory is consistent with experiments, at least for the solar scale experiments. Okay, so this can tell us, give us kind of bridge between experiments and the theory. So let me explain this. Okay, so formalism starts with the stress energy tensor of the perfect fluid form. So we have energy density rho, and in this case rest mass density, and the pressure P here, and specific energy density pi. Okay, and also of course 3 velocity. So out of this 3 velocity, we can construct 4 velocity. And stress energy tensor is constructed in this way. Okay, and so the matter variables are given by these 3 plus 3, so the 6 variables. Okay, then we introduce a post-Newtonian bookkeeping parameter epsilon, so that we consider a slow motion. So the v is order epsilon, and the time derivative is order epsilon compared to spatial derivative, and energy density is order epsilon square, and so on. Then we expand everything in terms of epsilon. Okay, and for example, metric in the lowest order we have a Newtonian metric, so -1 plus 2 times Newtonian potential, and the G0I is 0 at the lowest order, and Gij is delta ij. Okay, so we consider on top of this we consider correction to this at the leading non-trivial order. This is a post-Newtonian expansion. Then we introduce many potentials like U and psi and B and so on. And in this way, these are definitions. And in some textbook, these potentials are defined in the integral form. But sometimes it's convenient to define in differential form. So I wrote down, I defined potential by differential form, okay, differential way, okay? Differential equations, okay. And of course, integral form can be obtained by these relations very easily. Then we introduce coefficients here and there, okay, and gamma and alpha 1, alpha 2, alpha 3, and so on, and beta and so on. And they are so if we have a theory of gravity, we can compute these parameters, and from experiments that we have a constraint on these parameters, so that this formalism can play a role of kind of a bridge between experiments and theory. Okay. By the way, in the standard PPN formalism, theta b, this one is said to be 0 by using the time diffeomorphism invariance. But some theory does not enjoy does not have time differential invariance. So that in that case, we need to keep this theta b. But here I assume the spatial differential to fix the gauge. Okay. So for details, please have a look at this paper, for example. Okay. And then we have residual symmetry, residual gauge freedom. If we have a 4D differential. And then we can set theta b to be 0 if we want. Yes, but yes, so theta b can be set by time differential. But in general, we cannot if you have only 3D differential. Okay, so we have 10 standard PPN parameters plus 1 sometimes, and among them only 10 are observable parameters. Okay, and theta b is not observable if matter action is 4D differential invariant, or approximately 4D differential invariant. Okay, at least matter sector should satisfy Lorentz invariance with a very high precision, and we expect that the 4D differential is also a good, at least in a good approximation asymmetry of the matter action. In that case, we cannot probe this parameter, but we can probe these 10 parameters and put the constraints. And in GR, general relativity, we have these parameters, okay, values of these parameters. Gamma is 1, beta is 1, all others are 0. And theta b is gauge freedom, so we can set it to be 0. Okay. And these parameters can be constrained by experiments. And for example, gamma, as I said, the gamma is 1 for general relativity, so the deviation from 1 is constrained in this way. Okay, this is a very good constraint, 10 to minus 5, and beta minus 1 is also a constraint to be of order 10 to minus 5 or 10 to minus 10 to minus 4, something like that. And there are many other constraints. But one thing that I want to mention here is that sometimes people mix up constraints on PPN parameters and analog of PPN parameters. Okay. These parameters with hat is kind of analog of PPN parameter in the strong gravity regime. Okay. And in this strong gravity regime, the PPN expansion, parameterized post-Newtonian does not hold, cannot be applied. So the theta hat is not really set. Hat is not Guzai itself, but there is a kind of analog with in the strong gravity limit. And there are some limits, okay. But we should not confuse with these two, okay. Anyway, there are many constraints. Okay. Then given some theory, we can put the constraint. We can compute the each parameters, and then we can immediately get a constraint on your favorite theory. Okay. So let me explain how to do that for scalar-tensor theory. A simple one, scalar-tensor theory. Okay. So the basic variable in this case is metric, and this is implied by the Einstein's equivalence principle. But we can also consider other fields if we do not consider a GR. Okay, and in the case of scalar-tensor theory, we have metric and scalar, and of course we have matter. Then the action is given by this Einstein. So that this is scalar curvature, which is scalar. But in the case of Einstein gravity, this coefficient is constant. But here, phi, scalar field. Okay, and then we have kinetic action for scalar field with some function omega, and then we have equation motion for phi and metric. Okay, so we have these two sets of equations. I mean, for as a basic equations. Okay, by combining with matter, we can solve the equations. Okay, then compute the ppn parameters. Okay, so first we introduce ppn expansion by employing ppn metric with theta b equals 0 because this theory is for the differential invariant. Okay, and then we also expand scalar field by epsilon. In this case, up to fourth order. They introduce some coefficient, gamma phi and CUU and so on. These potentials were already defined here. Okay, we use the same potentials, but independent parameters. Okay, and we assume the perfect Fourier form for T mu nu, and then we can compute parameters. Those parameters, among them 10 are observables and also G Newton. Here, Newton's constant is the derived quantity. Okay, so we need to compute G Newton. Okay, and we can compute also other parameters, but they are not observable. We cannot observe them. Okay, so we are interested in this 10 plus 1. Okay, so we start from the equation motion for phi up at second order, and there is a component of Einstein equation, G equation motion at this order. Then we can determine G Newton and the gamma phi. Gamma phi is coefficient here. Then we can go on to different equation motion at a different order. So this is a trace of ij component of the metric equation up to at the second order. Then we can solve this with respect to gamma to give this. This is observable. Okay, and also we can compute alpha 1 and so on. We can compute everything. Then in the end, we have gamma, which is different from 1, and beta, which is different from 1, and all others are 0. Okay, so by experiments and like this, these constraints limits on ppn parameters. I mean, especially these two, tells us the constraints on this combination and this combination. Okay, in this way, ppn formalism plays a role of a bridge between theory and the experiment. Okay, so let me summarize ppn formalism. So the one can go beyond GR, but only to the extent that is consistent with all experimental constraints, of course. And there are many theories and experiments. And if we consider combination of theories and experiments, there are so many. But thanks to the ppn formalism, possible deviation from GR at the solar system scales are universally constrained by experiments. And this formalism has 10 ppn parameters and G Newton, and they can be computed from theories and then are constrained by solar system scale experiments. Okay, and we have a table of constraints on ppn parameters. By using this, we can get the constraint on the theory. From theory side, we can compute the ppn parameters, and I showed a sketch of computation in the simple scalar tensor theories. So after you go home, you can pick up your favorite theory, compute the ppn parameters, and use this table to test your favorite theories. Hopefully. Okay. So here up to here we now know. I mean, so here we from Lovelock theorem we know how to modify GR, what to do, and then from ppn we know to what extent we can modify gravity. So let me explain some theories. Okay. So EFT scalar tensor theory and massive gravity. Okay. As far as I have time. Okay. Okay, so here EFT or effective field theory is motivated by the following things. Okay, there are many modified gravity theories. Okay, And when we encounter a new modified gravity theory, there are at least 3 checkpoints. Okay. So first, what are the physical degrees of freedom? And second, how do they interact? Okay. And then what is the regime of validity? Okay. If 2 theories or more theories give the same answers to all 3 questions, then they are actually the same, even if they look different. So I think there should be some universal description, okay, independent of the appearance. Okay, so EFT or effective field theory is such a framework. Okay, and in this section, I'd like to talk about the EFT of scalar tensor theories. So let me explain a bit about the scalar tensor theory. Okay, as we have already seen in the simple example, scalar tensor theories are described by metric and the scalar field. And so the history of scalar tensor theory was started by Jordan and Brown-Stieke and Bergman and Wagner. So the history is relatively long. Okay. But most general scalar tensor theory with second order covariant equation motion was derived by Horndeski in 1974. And more recently, those theories beyond Horndeski was found by these people. Okay? And indeed, effective field theory can describe all of them, and actually more. More general scalar tensor theories can be described by EFT. Okay? So that's why I want to explain EFT here. Okay? So the the way how to construct EFT is as follows, especially around the inflationary background or for dark energy. Okay. So here we assume that the time differ is broken because the universe is expanding, and also during inflation, for example, we want to stop inflation. So if we have inflation is accelerating universe, kind of exponential expansion. And if it continues forever, universe will be empty. So we want to stop it at some point, and we want to stop it almost at the same time everywhere. Otherwise, a universe after inflation will be inhomogeneous. We want to stop inflation at almost the same time. Okay, and for that purpose, we need a kind of field that counts the times, that measures times remaining until the end of inflation. So and that one should have a time derivative, because the value of this scalar, this field should change in time. Okay. So in this sense, the time differ is broken, but we can keep special differ. Okay. This is a kind of asymmetry breaking pattern. And all terms that respect special differ must be included in the EFT action. Okay? And then after that, we can perform derivative expansion and the particle expansion. Then later, if we want, we can recover differ invariance by introducing kind of Namb-Golson boson. Okay? So this is how we can construct EFT. Okay? And the simplest one is the ghost condensate, which I proposed some years ago. So I'd like to start with this because this is the simplest. Okay. And ghost condensate is analog of Higgs mechanism in gravity. So let me compare these two. Okay. Higgs mechanism has a wave of scalar field as an order parameter, and we consider a potential like this. And in the case of ghost condensate, we consider wave of derivative scalar field as order parameter. So we consider kinetic term like this instead of potential. Okay. In both cases, we have top of the hill and the bottom. Okay. And at the top of the hill, we have instability like tachyon or ghost. And but we have a nice place where first derivative is 0 and the second derivative is positive. Okay, here and there, or here and there. So we can live there. There, either gauge symmetry or time translation symmetry are broken spontaneously, and the gauge force or gravity are modified in an interesting way. So this is the idea. And but I will not go into details about the phenomenology of this. Instead, I'd like to explain how to construct the effective field theory of Gauss condensate in a systematic way, because this is basics for the construction of EFT with inflation and dark energy. Okay, so let me explain this. So we assume that the background is characterized by non-vanishing wave or derivative scalar field. This is non-zero, and also time-like, because we don't want to break spatial diffusion. Our universe is homogeneous isotropic. Okay? And for simplicity, let's consider that the background metric is maximally symmetric, either Minkowski or Dojita. Then we can show that the action describing the perturbation around this background is universally given by this. So let me explain this. This is completely universal. So because of this assumption, we can choose the time coordinate so that it agrees with the scalar field itself. Okay. This means that the fluctuation of scalar field is set to 0 by gauge choice. This is sometimes called unitary gauge. Then the decidual symmetry is spatial diffusion. We can change a spatial coordinate to any function of time and space. And then we can write down most general action invariant under this decidual symmetry. Okay. After that, if we want, we can recover the covariance by introducing Nambu-Gosson boson pi by undoing unitary gauge. Okay, I'll do this later. Okay. So let's start with, for simplicity, flat background, G mu nu equal eta mu nu plus H mu nu, which is perturbation. Okay. Then we know that under infinitesimal coordinate transformation, H mu nu transform in this way. Xi mu is a gauge vector, gauge parameter. Okay. Then we should consider this one, so spatial diffusion, so that we should restrict our consideration to Xi I. So we should set Xi 0 to be 0. Then the H00 is invariant, H0i transform in this way, Hij transform in this way. Okay, because Xi 0 is 0, yes, this is 0. Okay, so when we write down most general action invariant under this is a symmetry, we can use H00, okay, because this is invariant. Okay, we can square it, and we should start from second order because we are assuming that Minkowski spacetime, Minkowski background is good background, so should satisfy equation motion. If we have a first order term, that gives us a equation motion for the background, and that should be 0 by this assumption. Okay, we are considering a Minkowski background for simplicity here. Okay, and but we cannot use H0i square because this is not invariant. Okay, we cannot use Hij square again because this is not invariant. But we can combine them to form an invariant combination. So first, take a time derivative of this, and then spatial derivative of this, and then combine in this way. Then this is invariant. Okay, so we can square this, and this is a square of trace, and this is a trace of square. Okay, so there are two combinations. By combining 3, we have this kind of action. Of course, we should include Einstein reduction because this is invariant under all diffusion, including spatial diffusion. Okay, so this is completely universal. And in principle, we have higher order terms, but later I'll show you that this is we can ignore them. Okay. Now the action for pi, which is Nambu-Gosson boson, can be obtained by promoting broken symmetry parameter and broken gauge parameter. So the Xi 0 we didn't use here, but now we promote Xi 0 to physical field, Nambu-Gosson boson. Then H00 transform in this way, Kij transform in this way. So just plug this to here and plug this to here, and there we get this. This is what I said here. So by these two assumptions, we get this. This is completely universal. Okay. Also, we can show that the terms in ... can be ignored. In order to do that, let's do the kind of scaling analysis. Let's multiply energy scale by some factor r, constant r, and then the dt goes like 1 over r because of the relation between energy and time. And spatial coordinates should go like this, because if we consider this action and set the metric perturbation to be 0, we get pi dot square here. And here, second spatial derivative squared, also this is a second spatial derivative squared. So we have this kind of action. This means that first time derivative should balance with the second spatial derivative. So the spatial coordinate should be square root of time coordinate, in a sense. So this should be square root of this. Namely, this must be minus 1/2. Okay. Then, assuming that this is invariant under scaling, we can show that the pi should scale like this. Okay. So that when we change energy scale, say that when we multiply energy by 1/2, then the pi scales like 1/2 to 1/4. Okay, so we know how pi scales when we change energy scale. Okay, by using this scaling analysis, scaling dimensions, we can estimate how, for example, this kind of operator, nonlinear operator in here, this is there here, but how this operator scales as we change energy scale. It turned out that this scales like r to 1/4, like this. Okay, so that as we lower energy, and this importance of this becomes less and less. Okay, on the other hand, these two terms are always the same. Okay, because we demanded that these two are invariant under scaling. Okay, so this means that this term is irrelevant, and so at low energy we can ignore them. Or at least we can consider this as a correction to these two. Okay. So in this sense, we have good low energy effectivity theory, and we can make a robust prediction. For example, we can construct the inflation model and make a robust prediction. Okay. And now I want to extend this to the expanding background. Now, so far we were talking about Minkowski background. Okay, non-expanding background. It's straightforward. This expand to generalize this to the general Lemaitre-Robertson-Walker expanding universe in the following way. This was done by these smart people, and I'm just reviewing this. Okay, and so the symmetry breaking pattern is the same as before. So that we want to have action invariant under spatial differ. Okay, xi becomes arbitrary function time and x. Okay. And then the ingredients in the action are like this. Okay, of course, the metric, inverse of the metric, curvature, covariant derivative, and t, because t is invariant under this. Okay, and also we can use derivative of t. Okay, for example, first derivative of t give us this one, Kronecker delta mu 0. 0 is upstairs, which is important, and also we can construct unit normal vector like this. This is actually this vector is orthogonal to constant time surface, actually. And also we can construct the G00 upstairs by contracting G mu nu with this twice. Okay, and also we can construct spatial metric by this. Okay, because this is unit norm, and this is kind of rank of this is 3. Okay, so and from the second derivative of t, we can construct the extrinsic curvature. Previously, we had this is actually extrinsic curvature, but at the linear level around Minkowski. In general, we have this expression. Okay. Then in the unitary gauge, action should be written in this way. Okay. So the some scalar made of time and the Kronecker delta, extrinsic curvature, metric, inverse metric, covariant derivative, and curvature. And we can construct scalar made of them, and then integrate over space-time. That's all. This is completely general action in the unitary gauge. Then but this is too general to be useful, so that we usually perform a derivative expansion and a perturbative expansion. Okay, if we do that, we have this kind of action. Okay, around the Friedman background. Okay. Then we can introduce Nabu-Gosson boson pi by undoing unitary gauge as before. The result is this one. After taking the decoupling limit, where we ignore the metric perturbation. Okay, And this is completely universal as far as we have a single field. Okay. And here, what is important is so-called sound speed, which is here, the ratio between the coefficient in front of the pi dot square and the gradient term. Okay, so this controls the speed of propagation for modes with high frequency. Okay, and indeed the dispersion relation is like this. And this also controls the amplitude, I mean the size of 3-point interactions, because CS square is in the denominator here. Okay, so CS square is when CS square is small, this becomes huge. Okay, so this becomes important when we compute the so-called non-Gaussianity, especially 3-point function. Okay, so this is what we derived already. So the CS square is here and also here. Okay, and we have only two types of 3-point interactions here. So when we compute 3-point correlation functions, we have contribution from here and here. So the 3-point function or bispectrum is characterized by coefficient in front of this guy and this guy. Okay, so one of them is sound speed square, because this is here. So that when CS square is small, then the non-Gaussianity, namely the size of 3-point function, becomes large. Okay, so this controls the size of non-Gaussianity. There is one more parameter, which is C3 here. This controls the shape of non-Gaussianity. Okay, so this is a kind of plot for the shape of 3-point functions as a function of ratio between among 3 momenta. We go to the Fourier space, and because of momentum conservation, the sum of 3 momenta should be 0. So we have 2 momenta basically, or we have a triangle. Triangle is characterized by length of each side. So the, K1, K2, K3, and we take a ratio. So that we have 2 ratios, and this is plot of the bispectrum as a function of 2 ratios. Okay, so they have different shapes, but parameterized by only one parameter. Okay, when C3 equals 0, this is so-called prototype of the so-called equilateral type shape. And when C3 equals minus 3.6, then this is the prototype of the so-called orthogonal shape. Okay, all other shapes are linear combination of them. Okay, so non-Gaussianity is 3-point functions, 3-point correlation functions is completely characterized by two parameters. Okay, originally non-Gaussianity is just saying that not Gaussian. So in principle we have infinite number of parameters, but by assuming the symmetry breaking pattern, we show that we have only 2 parameters. So this is the strength of this EFT approach. Okay, so let me summarize the EFT approach. Okay, so the Gauss condensate is a universal description of scalar tensor theories around Minkowski and Logit background. And the extension of Gauss condensate to the Friedmann-Lemaitre-Robertson-Walker expanding background result in the EFT of inflation and dark energy. And this EFT provides a universal description of all known scalar tensor theories, including Horndeski theories and Dosto theory and more. Okay, so if I have time, I'd like to explain briefly the massive gravity. Okay. So let me go on. And as I briefly mentioned, massive gravity was motivated by the very kind of fundamental question. Okay. So namely, can graviton have mass? Spin to field. Okay, so this is the basic question in the classical field theory. Okay, and this has relatively long history, and the answer to this question turned out to be time dependent. Sometimes people thought it's okay, sometimes no. So I put the seesaw here or balance. Okay, the first answer to this question was of course yes. Otherwise, history didn't start. So the first answer was yes, and provided by Fierce and Pauli, famous people, and they found a unique linear theory without instabilities. Okay, and unique in the sense that we have, compared to general relativity, we have only one additional parameter. Okay, which is mass of graviton. Okay, general relativity in GR, the graviton has 0 mass. But in this theory, we have mass. So that this is only one parameter. Okay. Then after some years, these people came up, VDVZ, and they showed that the massless limit of this theory does not agree with GR. Okay. As I said, this is GR plus graviton mass. So if we set mass to be 0 from the beginning, we recover GR. But if we keep non-zero mass and take the limit, then they show that the massless limit is not GR. So there's a discontinuity, okay, at m equals 0. Okay, and indeed this difference is order 1, and indeed one of the ppn parameter is different from GR value by order 1, and as we already showed, seeing that the deviation of GR is very strongly constrained. Okay, so if their result is correct both mathematically and physically, then the massive gravity would be excluded by experiment, however small graviton mass is. That's bad. Okay, but 2 years later, Einstein came up and he showed that in the massless limit, as we send the graviton mass to smaller and smaller and smaller value, then the linear approximation completely breaks down. Okay, we need to take into account nonlinearity. If we do that, then the massless limit agrees with GR. Okay, but in order to do that, we need to perform nonlinear analysis. Okay, basically, what he was saying is that if we ask the right question, physical question, then the physical answer is continuous as we change the parameter of the theory. Okay, this is what he said. So now answer is yes, but then in the same year, Borley and Deza said no. They found that the same kind of nonlinearity that saved the fierce power theory caused a problem. Okay, when we consider nonlinear theory, then kind of extra degree freedom appears. Okay, so this fierce power theory have 5 degree freedom, and this was achieved by kind of fine tuning. Okay, and this fine tuning is detuned by going to nonlinear order. Okay, this is what they show, and since then, for almost 40 years, people believe that there is no way to give a mass to graviton. Okay, and then fortunately, in 2010, Duram, Gabadate, and Torre found a way out. They found the first example of nonlinear massive gravity without the Borley-Deza ghost. Okay, this ghost instability is called Borley-Deza ghost or BB ghost. Okay, so now we know the answer to this question, so that we can give a mass to graviton, at least theoretically. There are some discussions about more fundamental questions like positivity bounds and so on, but today I'm not going to talk about this. Okay. Instead, I'd like to talk about the second question. Can we have acceleration without dark energy? Okay, namely cosmological question. Okay. But first answer regarding this theory, regarding cosmology in this theory, was bad. Actually, the authors of this paper included these 3 people. Okay, and they found that there is no flat expanding universe if we assume homogeneity and isotropy. Okay, so this is bad. Okay. And it was a time when I started to think about this theory with my friends. Fortunately, we found a way out, and we found that although the flat expanding universe does not exist, but open Friedman universe is okay. So open universe, namely the negatively curved space, can expand. Okay, and so this is good. And also, it turned out that by slightly extend the theory, namely slightly extend the so-called physical metric from the Minkowski metric to something else, say logita, then we can find all types of Friedman-Lemaitre-Robertson-Walker universe. Okay, open, closed, and flat. Okay, so they are good. They are good results. And but as you can expect from the fact that I put seesaw or balance, the answer changes from time to time. Okay, indeed, in the year after the discovery of these solutions, we found that they have instability. kind of new type of instability, because we found a kind of nonlinear instability that is different from the Bollinger delta ghost, because this is within 5 degrees of freedom. And also this is different from the so-called Higgs ghost, which is linear instability. Okay, so this is nonlinear instability, and which is new. And so we found a new phenomenon in massive gravity. So in a sense, we were happy, but at the same time, we were sad because we killed our solution. Kind of mixed feeling. So naturally, we tried to find a way out. Okay. One possibility was to find a new type of solution in the same theory, but because we found that all homogeneous and isotropic universe in this theory is unstable, so that we need to break either homogeneity or isotropy. Okay, we decided to break isotropy. So this is a so-called anisotropic Friedman-Robertson-Walker universe. So that we have two metrics, G mu nu and the so-called physical metric. Both of them are each of them is homogeneous and isotropic. But if put them together, they do not share the same symmetry, and rotational symmetry here and rotational symmetry here are not the same. So in this sense, the whole system breaks the isotropic universe, isotropy. But our universe itself, if we look at them, if we look at only our universe, it is isotropic and homogeneous. So that's why we call it an isotropic Friedman-Robertson-Walker universe. Okay. Anyway, this is a new type of solutions. But another possibility is to change the theory. One possibility is what we call the minimal theory of massive gravity. Okay. So in this theory, we have two physical degree of freedom, and we have exactly the same expanding background as in DRGT. And there are no BD ghost, no Higgs ghost, and no nonlinear ghost. And also the positivity bound does not apply. And the construction is conceptually simple. And we can find this theory by only 3 steps from DRGT. Okay. And this theory may fit the data better, but maybe I'll skip this. And also we can find black hole solution and stars, at least for spherical symmetry case. In rotational case, I mean, there may be some modification that can be probed by say gravitational waves. And we want to think about this later, but now, okay, so now I'd like to talk about the R universe based on this. So actually this theory, if we slightly extend to make graviton mass and parameters to be function of, say, another scalar field phi, so that graviton mass can change values. Okay. So initially, I want to consider large value, say, for example, during inflation, and also after for a while after inflation, up to time Tm. Okay. This is after reheating, but before BBN, Big Bang nucleosynthesis. Okay, and then until Tm, graviton mass is large, but becomes small after that, in order to satisfy the bound from the LIGO. Okay, gravitational waves. Okay, and in this case, we can have amplified and tilted prime model gravitational waves. Okay, so let me explain the reason. First, because graviton has a mass, then the red part of the spectrum of gravitational waves is suppressed, because if the momentum of graviton is lower than or comparable to the graviton mass, then the amplitude should be suppressed because it is massive, okay, compared to massless case. But in the blue part, namely the or UV part, namely when the momentum is much higher than graviton mass, then that mode doesn't care the value of graviton mass, so the amplitude is as high as in the case of massless case, namely GR. So in this sense, red part of the spectrum is suppressed. Then we have a blue spectrum. But suppression of red part is not so nice. But what is nice about this setup is that we can enhance the amplitude, okay? Because graviton is massive until Tm, meaning that energy density scales like 1 over A cube, where A is the scale factor of the universe, like 1 over the volume. Okay, compared to GR, in GR, I mean, we have energy density of gravitational waves, which scales like 1 over A to 4, and A, I mean, becomes larger and larger. So the compared to GR, decay is slower. So the compared to GR, we have amplification. So that even after imposing constraint from CMB here, we may have a spectrum like this, or a spectrum like this, because amplitude is enhanced and also spectrum is blue. And then this part or this part can be probed by experiment. Okay, this is a region where we can probe. For example, here, if we are here, then all three detectors can detect the gravitational waves from inflation, enhanced by this theory, minimal theory of massive gravity. Okay, so this theory may be one possible way out, and but you may think that this theory has two metrics, G mu nu, and also the so-called fiduciary metric, which is fixed by the theory. You may wonder whether we can promote second metric to dynamical one, and recently we did. Okay, so this is a minimal theory by gravity. Okay, so in this case we have two metrics, and we have 4 physical degree of freedom, which corresponds to massless graviton, massless gravitation waves, and the massive gravitation waves. Okay, and we have exactly the same freedom and Robertson-Walker background as in Hassan-Rosen bigravity, which is a bigravity version of DRGT. Okay, and there is no instability, completely stable. And so therefore, this is the very first example of completely stable and cosmologically viable theory of nonlinear bigravity. And this can provide a testing ground for gravitational phenomena. For example, gravitational oscillations that can be probed by gravitational waves. Okay, so this may be another way out. So let me summarize massive gravity. So we have a nonlinear massive gravity found by DRGT, and this is free from BD ghost, Brodel ghost. However, when we consider expanding a universe, there is no closed and flat universe if we assume homogeneity and isotropy. Unfortunately, an open universe with self-acceleration was found, and also we can generalize this to closed and flat and expanding universe by slightly extending the theory. But unfortunately, all of them in this theory are unstable, okay, or strongly coupled. Okay, so the stable cosmology requires either new class of cosmological solution in the same theory or to change the theory. Okay, and the minimal theory of massive gravity, MTMG, and minimal theory of bigravity, MTBG, provide nonlinear completion of DRGT or Hassan-Rosen bigravity, self-accelerating cosmology. Okay, so in this cosmology, universe can be, expansion of the universe can be accelerated without dark energy, because graviton mass plays the role of effective cosmological constant. So this may be interesting. Okay, so let me summarize my talk. Okay, so there are at least 3 motivations to go beyond GR: mystery in the universe, quantum gravity, and understanding GR itself. And the GR assumes Einstein's equivalence principle and only G mu nu assumption. Then we end up with, of course, GR at least at low energy. And then by performing a Hamilton analysis, we have shown that the number of local physical degree of freedom in GR is 2 at a fully nonlinear order. And the GR is unique if we assume these 4 assumptions: 4 dimensions, differential invariance, and metric only, and up to second order equation of motion of this form. Okay, and therefore modification GR requires at least one of the following, namely extra dimension, extra degree of freedom, Lorentz violation, or non-pseudo-Riemannian geometry. Okay, and thanks to so from this we know how to modify GR, but to what extent we can modify. And thanks to this PPN formalism, possible deviation from a GR at the solar system scale are universally constrained by experiments. So we know, at least in the solar system, to what extent we can modify GR. then I explained the ghost condensate, and then the generalization of this to the expanding universe, which are called EFT of inflation or inflation of dark energy. Okay, and I didn't have time to explain Hodge-related gravity, and but instead I talked about massive gravity. Okay, so DRGT theory realizes nonlinear massive gravity without Borg-Dirac ghost. But stable cosmology in massive gravity requires either either breaking. So we consider more different cosmological solution, breaking either homogeneity or isotropy, or we need to extend the theory, such as we need to consider such theories such as MTMG or MTBG. Okay, let me stop here. But I want to maybe make some comments. Okay, so this is what I already showed here. So I think because of this kind of experiments, I think it's a very good time to think about the modification of gravity, because I mean, so we have new data and new theories, and we know how to go beyond GR from Lovelock theorem. We need at least one of them, and there are many possibilities to explore. And either addressing mysteries in the universe, constructing theory of quantum gravity, or understanding GR. Maybe I hope some of you in the audience have new theories to address. I mean, to motivated by one of them or some of them. Okay. Okay, that's all. Thank you very much.
Thank you, sir, for your wonderful and exciting presentation, sir. If you allow, we can start our discussion session. So we have got few questions.
Yes.
So I can start our discussion session. First question: is the standard model of particle physics is inconsistent with that of general relativity?
Of course, they are compatible with each other. Yes. So we can combine GR with the standard model of particle physics. Yes. I mean, the GR satisfies Einstein's equivalence principle, and so basically if we go to the free falling frame or local Lorentz frame, then we recover special relativity. And the standard model of particle physics is based on special relativity, so they are compatible with each other. Yes. We can combine standard model and general relativity. But when we try to quantize gravity, we have a difficulty. Yes. But we can quantize the standard model of particle physics in a GR setup. Yes. Sometimes we call it semi-classical approach.
So you have another question. So can string theory or loop quantum gravity unify general relativity and quantum mechanics?
Yes, I mean, that is an intention. Yes. So so string theory, I mean, is I think the strongest candidate for quantum gravity, which is supposed to unify general relativity and quantum theory. Yes. So hopefully in the future, I mean, the string theory is not completed, and yes, and we don't understand fully the string theory. But in the future, if we understand the string theory very well, maybe at that time, quantum. I mean, so the string theory can provide quantum gravity.
So thank you, sir. We have another question. So do the measurement rate of the change in high energy neutrino racing through Earth provides a record-breaking test of Einstein's special theory of relativity?
Racing through Earth provides the record-breaking test. Rate of change. Rate of change in high. What do you mean? Sorry, the speed of propagation or
As a measurement of the rate of change in high neutrinos racing through Earth. I think we can go next question.
Sure.
So, what is the spin form in quantum gravity, and can it lead us to a theory of everything?
Okay. So I think they are independent concepts. I mean, the theory of everything and spin form and okay, so spin form and yeah. So so spin form. I think I'm not very familiar with this, but I think microstructure of geometry in probably loop quantum gravity, and so in loop quantum gravity, I think so the hope is to quantize general relativity without changing too much the GR. And but it is not so it does not try to be a kind of a unified theory. Okay, and theories of everything by definition should be unified theory. We need to unify. I mean, so the standard model of particle physics and gravity and everything, right? And so they kind of defined concepts. Yeah, but yes, yeah. But
Yes, sir,
maybe
we have another question. Yeah, thank you. So, do graviton exist? Next
do
question.
gravitons?
Graviton.
Yes, I see. I see. Yeah, I think so, but I mean it depends. Yeah. So some people think that graviton may be just I mean so that yeah so effective degree of freedom like a phonon. I mean so when we consider phonon, I mean the fundamental degree of freedom is the phonon, but say yeah small. I mean so the atoms and so on, and that forms the material, and they oscillate, and we then but we can yes then phonon is kind of collective degree freedom, and some people think that graviton may be I mean collective degree freedom, effective degree freedom, but some people think that graviton may be fundamental, and so we don't know. Yeah.
Okay, sir, thank you. So, we have another question. So, can scalar tensor theory lead to asymptotic safe gravity?
That's interesting. Yeah, but yes, so the in asymptotic safe gravity is based on a kind of higher derivative gravity. I mean, in usually with just metric, but we can also consider in principle we can consider metric and scalar with a higher derivative terms in the action, and then in principle we can think about the asymptotic safe scenario based on that, and I think there are some people working on that. Yes. Yeah, but whether it is successful or not, we don't know yet. There is a possibility.
So, yeah, thank you, sir. We have another question. So, generally, a ghost field do not obey the spin statistics properties. How does their condensates matter, and what type of global symmetry is broken spontaneously?
Okay. So yes, here we are probably he's asking about ghost condensate, and but this ghost is not a Faddeev-Popov ghost. This ghost that I was talking about is a scalar field with a long sign kinetic term, and when I mean, so if we consider Higgs field, and Higgs has a negative mass square, so it is unstable. But if we are away from the top, then we have a stable minima, and mass square around there is okay, positive. Similarly, if we consider ghost condensate at the top of the kinetic energy, this is unstable, but we may have some stable place. That is ghost condensate, and so that is scalar. Okay, so boson. Okay.
Sir, we have another question. So,
Yes.
how is the stability of vacuum assured in the perturbative analysis?
Yeah, usually it depends on the situation, but usually perturbatively I mean, yeah, in gravity research on gravity, we start with some given theory, and then find say in this case probably vacuum solution, say Dojita or Minkowski background, then consider perturbation. Okay, then compute the action, second order action, to see if the kinetic term has a right answer, a correct sign, and also the sound speed square is positive, and so on. Then basically we see the stability analysis at the perturbative level. And sometimes some system which is stable at the linear level may become nonlinear and unstable at the nonlinear level. So sometimes we may have to be careful. Yes.
So thank you. So we have another question.
Sure.
So how does massive gravity affect Venus universe?
Which universe? Bianchi universe. Okay. Yeah, this is an interesting question. Yes, indeed. Yes, the Bianchi universe is a homogeneous and anisotropic universe, and so for example, in general relativity, this anisotropy, effective energy density of anisotropy decays like 1 over 8 to 4, 8 to 6, sorry, 8 to 6, okay, 1 over 8 to 6, okay, and because this is massless, okay. But on the other hand, in massive gravity, if we consider Bianchi and anisotropy, then anisotropy is, in a sense, both in GR and massive gravity, the anisotropy is, in a sense, the condensate of graviton, in a sense, in the homogeneous limit. And so the behavior is different because on one hand, in GR, this anisotropy like a massless graviton, which scales like 1 over 8 to 6. But on the other hand, in the case of massive gravity, it behaves like massive gravity, massive field. Okay, so I think if I remember correctly, effective energy density of anisotropy scale like 1 over a cube, if I remember correctly. So the behavior is different. Yes.
Okay, sir. Thank you. This may be the last question. So, yes. How can massive gravity tested experimentally?
Yeah, that's a good question. Indeed, so for example, this minimal theory of massive gravity. So I think that is completely stable, and gravitational mass can be small enough if we to satisfy the constraint from the propagation gravitational waves. But even after that, even after imposing that constraint, I think generation gravitational waves can be different. So if we consider generation mechanism of gravitational waves, say binary black holes and something like that, then we may be able to probe massive gravity. And also in the case of minimal theory of bigravity, we have both massless graviton and massive graviton, and they, similarly to the Newtonian oscillations, they can oscillate between them as gravitational waves propagate. And this may change the propagation, and this may also have some effect. And also the generation mechanism also changes. Yes, yeah. So gravitational waves is very interesting. Yes.
Yeah, thank you, sir, for your wonderful presentation and exciting discussion session, sir. I think our students and viewers have learned a lot of things about the gravity beyond the general relativity. So the main aim of our program is to motivate and encourage our students in this next type of research field. And I think some of our students will be motivated by your lecture and will join in this field. And hopefully they might solve the problem as we now have, and you have mentioned. And we think it will be a great opportunity for our students and the viewers to interact the scientists like you. So thanks again. And we have got another question. So not question, it's a comment. I can add this. So if the kinetic term of the scalar is with a wrong sign, does the Hamiltonian have a lower bound?
No. Yeah, if we consider just the wrong sign kinetic term for scalar, then we don't have, so the Hamiltonian is not bounded from below. But if we condense at stable minima, then the Hamiltonian is bounded from below, around that minima, at least in the regime of validity of effective field theory.
So maybe he changed his question lastly. We haven't understood. So the question he corrected now. The rate of change in neutrino in the previous question refers to the rate of change in flavors of neutrinos.
I see.
For example, neutrino oscillation.
Yeah. So that's a good question. So from the neutron oscillation, we can actually constrain the some Lorentz violating operators in the neutron sector, and that can so that of course Lorentz violating operator in the matter sector, neutron sector, for example, and gravity in principle independent. But if we modify gravity, sometimes gravity can induce the Lorentz violating operator in the matter sector, and so that indirectly we may be able to probe some properties of gravity. Yeah, good question.
Sir, yeah, thank you. I think everybody have enjoyed your lecture and learned a lot of
Thank you
things
very much.
about gravity beyond the general relativity, and that will be helpful for their future life also. So we found that this webinar give us so much a variety of knowledge from different fields, and we're trying to bring more researcher in our webinar. And thanks again for helping us by giving us time, and our students and viewers are motivated by your lecture. So thanks again, and I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitations. And hopefully in near future we'll arrange another webinar, and after the COVID we'll definitely invite you for a face-to-face session. Bye, sir.
Thank you very much.
Have a nice day, sir. Bye.